Welcome to Eureka Math. I'm Mr. Shankel. I'm going to be helping you today with Module 1, Lesson 12. Let's get started. Okay, we're going to be working with choosing units today, and we'll start off with exercise 1. A certain brand of MP3 player will display how long it will take to play through its entire music library. If the maximum number of songs the MP3 player can hold is 1,000 and the average song length is 4 minutes, would you want the time displayed in terms of seconds, days, or years worth of music? So in order to make our decision here, we're going to find out what the actual number would be for each of these possible lengths, seconds, days, or years, and then we'll decide based on the numbers we get. So we've got to do some calculating in order to get there. So let's say we have 1,000. Oh, that's a big pen there. Okay, so 1,000. Let's say we have 1,000 songs, and each of them are 4 minutes long. All right, and the first one we'll do is we'll turn these into seconds. So in order to do that, I'm going to multiply by a conversion factor, which will turn my minutes into seconds. And so I just need to know how many seconds are in a minute, and I remember that there are 60 seconds in 1 minute. And then I can go ahead and multiply. And I want you to see what happens when we multiply. The minutes will cancel each other out, and I'm going to be left with seconds. So 1,000 times 4 is 4,000, and 4,000 times 6 is 24,000. So I'm going to have 24,000 seconds. So that's our first one. And then let's see what it would be if we use days. If I use days, let's see. I'm going to have 1,000 songs. They're 4 minutes each on average, and I need to change now into days. So I'm going to change my minutes into hours, and I know that there are 60 minutes in 1 hour. And then I'm going to change my hours into days. And there are 24 hours in 1 day. And then when I go ahead and calculate here and multiply, the minutes will cancel, the hours will cancel, and I'm left with days. So I just need to multiply. 1,000 times 4 is going to give me 4,000. So let me see if I can sneak this in here. 4,000. And on the bottom I have 60 times 24, which is 1,440. And then I can do that division. 4,000 divided by 1,440 is about 2.8 days. So this is equal to 2.8 days. Okay, and that's our second one. So we have 24,000 seconds and 2.8 days so far. And now we need to find out how many years that would be. And hopefully you can see that years is going to be maybe not something we want, but we're going to figure it out and to see what it is. So I've got still 1,000 songs. I'm going to multiply by 4 minutes each. And then I need to change my minutes into hours. And again, 60 minutes in 1 hour. And then I need to change my hours into days. And there are 24 hours in 1 day. And then I need to change my days into years. And there are, I don't know if I'm going to be able to fit it, 365.25, but we'll just say 365 days in 1 year. Okay, and so when we do that, we get some canceling again. The minutes cancel with the minutes, the hours cancel out, the days cancel out, and I'm left with years, and that's what I want. So 1,000 times 4 gives me 4,000 on the top, and on the bottom, 60 times 24 times 365 is 525,600. Okay, and then if I divide that out, let me do that for us right now. If I divide 4,000 divided by 525,600, I get this answer. So here's my number of years. 0.008, if I round it, years. Okay, so there's our answer in years. So the question then is, what would we rather see? Would we rather see this MP3 player holds 24,000 seconds worth of songs? Would we rather hear that this MP3 player holds 2.8 days worth of songs? Or would we rather hear that this MP3 player holds 8 thousandths of a year worth of songs? I think we can quickly eliminate 8 thousandths of a year. That doesn't sound like I really know what that means. I don't know what 8 thousandths of a year would be. 24,000 seconds, a little hard to understand. I think our best is 2.8 days. I can clearly understand that. A little less than 3 days worth of music. Okay, it's exercise 1. Exercise 2. You have been asked to make frosted cupcakes to sell at a school fundraiser. Each frosted cupcake contains about 20 grams of sugar. Bake sale coordinators expect 500 people will attend the event. Assume everyone who attends will buy a cupcake. Does it make sense to buy sugar in grams, pounds, or tons? All right, so let's do some work to figure out what these numbers would be for grams, pounds, and tons. Okay, so let's start with grams. This will be an easy one. If we start with grams, I have 500 people, and each one's going to buy a cupcake that's going to have 20 grams, and that's it. I just need to multiply. 500 times 20 is 10,000 grams. Okay, so there's our first one, 10,000 grams. All right, next, let's change into pounds. So I'm going to use the same 500 people. Each person is going to buy one cupcake, which is 20 grams. And then I want to change my grams into pounds. So we'll need a conversion factor here. And you can look this up online, but the conversion factor is there are come on, work for me. 0.002 pounds in 1 gram. 0.002 pounds in 1 gram. And then, using the unit analysis, I can cancel my grams. I get pounds, that's what I want. And then I just have to multiply 500 times 20 times 0.02, and that turns out to be 20 pounds. That one sounds nice. I like that. So there's our second one. And then let's see what happens if we turn this into tons. So we're going to use the same 500 people. They're each going to buy one cupcake, which is worth 20 grams of sugar. We're going to change our grams into pounds again. 0.002 pounds in 1 gram. And then we're going to change our pounds into tons. And there are 2,000 pounds in 1 ton. If you don't know those conversion factors, you can look those up online. But now I can eliminate grams and pounds, and I'm left with tons, which is what I want. And when I multiply, I get 20 divided by 2,000, which is 0.01 tons. Okay, and there's our 3 options. Would you rather, if you're buying sugar, would you rather buy it in grams? Let's say, go to the store and say I need 10,000 grams of sugar, or 20 pounds of sugar, or I need 1/100th of a ton. Well, I think probably 20 pounds would be the easiest since it's sold in pounds usually. So there we go. There's exercise number 2. Number 3, the seafloor spreads at a rate of approximately 10 centimeters per year. If you were to collect data on the spread of the seafloor each week, which unit should you use to record your data? Well, we're just going to test some things here. 10 centimeters per year, and we want to see what the spread is every week. So I need to figure out how much would it spread every week in centimeters. We'll try that first. So let's see how many centimeters per week this is. In order to do that, I'm going to start with my with my 10 centimeters every 1 year. And then I want to get rid of the years. So my years are going to come up on top. I want to change them into weeks. And I know that there are 52 weeks in 1 year. And now I can multiply. So the years cancel. I get centimeters per week. And so 10 divided by 52 is 0.19 centimeters per week. Okay, so there's one possibility. That's it's okay. It's not bad. Let's try another one. Let's change this time into let's go meters. Let's see what meters is. If I start with 10 centimeters per 1 year, I still want to change it into per week. So I'm going to change the years into weeks, and I know that there are 52 weeks in 1 year. And then I also want to make one more conversion. This time I want to get rid of centimeters, and I want to change them into meters. And there are 100 centimeters in 1 meter. So let's see what we get here. The years still cancel. The centimeters now cancel. And I get meters per week, which is what I wanted. And so now I'm going to have 10 on top divided by 52,000, which equals about 0.0002 meters per week. Oh, that got worse. That's more confusing. So let's try another. Let's do this. Let's go to millimeters. Let's get a little smaller than centimeters. So we've still got 10 centimeters every 1 year. We're going to change the years into weeks. There are 52 weeks in 1 year. That's my conversion factor. And then I want to get rid of centimeters and change them into millimeters. And I know that for every 1 centimeter there are 10 millimeters. So now when we analyze our units, the centimeters will cancel, the years will cancel, and I'm left with millimeters per week. So now 10 times 10 is 100 divided by 52, and 100 divided by 52 is 1.9 millimeters per week. And that one makes the most sense to me. A lot easier to understand. Every week that goes by, the seafloor spreads 1.9 millimeters, almost 2. All right, very good. Exercise 4. Okay, so we're going to use a giga electron volt here, and a giga electron volt is given by this unit, and it's actually equal to 1.783 times 10 to the negative 27th kilograms. And particle scientists have decided that instead of constantly referring to these really minuscule numbers, to assign a unit to that size. So that size is now known as a giga electron volt. And so we're going to show that the mass of the proton is 0.938 giga electron volts. Now, we don't know how many there are to begin with, so we're going to use some algebra here. We're going to say 1 giga electron volt, or 1.783 times 10 to the negative 27th, that's the giga electron volt, times x. X is going to be the number, the mass of the proton. Okay, so how many giga electron volts? The x is going to tell me how many of these. All right, so there's our x, and then that's going to be equal to the mass of a proton, 1.672622 times 10 to the negative 27th. Okay, and then using our algebra skills, we would isolate the x by dividing by this giga electron volt, 1.783 times 10 to the negative 27th. And whatever we do to one side, we have to do to the other. So 1.783 times 10 to the negative 27th. And when we divide that out, this side cancels and we get what we want, x equals, and when we divide 1.672622 divided by 1.783, we get approximately 0.938. Now, what do we do with the exponents here? These exponents have the same exponent, negative 27, so we would subtract, which would be 0. So that's times 1. So that's our answer. 0.938 giga electron volts is correct, and we've proven that to be the case. Okay, so using some algebra there to make sure that we understand that it's almost 1, the mass of one proton is almost 1 giga electron volt, which is this size. Okay, exercise 5. In popular science writing, a commonly used unit is the light year, or the distance light travels in 1 year. So we're going to use 1 year as 365.25 days to be really precise. So 1 light year equals a large amount of kilometers, or 9.46073 times 10 to the 12th kilometers. Our job is to figure out exercise 5. The distance of the nearest star, Proxima Centauri, to the Sun is approximately 4.013336473 times 10 to the 13th kilometers. Show that Proxima Centauri is 4.2421 light years from the Sun. So we're going to do something very similar to what we just did. We're going to take the distance of a light year, which was 9.46073 times 10 to the 12th, and we're going to multiply that by x. That's going to tell me how many light years the closest star is, and that's going to be equal to our distance from the nearest star to us, to the Sun, to our Sun. So this is 4.013336473 times 10 to the 13th power. All right, some big numbers here. We're just going to use our algebra and divide by 9.46073 times 10 to the 12th. And we're going to do the same thing over here, divided by 9.46073 times 10 to the 12th. And then with algebra, we see that this is just 1, or 1x, and that is equal to 4.013336473 times 10 to the 13th divided by 9.46073 times 10 to the 12th gives us 0.42410021 times, well, 10 to the 13th minus 12 is 10 to the 1st, or just 10. So then we move our decimal one place to the right, and we get x equals about 4 point, come on, 2421 light years. And there we are, and we have proven this. All right, that is lesson 12. I hope that helps. See you again next time.